we start with a phase that is tetragonal and paramagnetic. Then, as temperature goes down, we first see a transition from tetragonal to orthorhombic, then from paramagnetic to magnetically ordered, and this is the so-called parent compound. As you apply pressure or introduce foreign elements there, these two transitions are suppressed, and then we see superconductivity appearing. Now, how I plan to organize my next two talks. Today, I'll talk about superconductivity. Okay? And in 2 days, or actually tomorrow when we're going up to the sugar loaf, I'll tell you about this ordered state here. I don't have pictures of me in the bands, because you can download on the Google. You're very much more known than Pascal's band, so I will not have time to wake you up. Okay? So today I want to talk about superconductivity, and before the end of the lecture, I will go back to the point that was discussed during Gil's talk about why superconductors superconduct. Okay? So as I told you, the magnetically ordered state has this spin-density wave, where spins go up, the spins are parallel along one direction and antiparallel along the other one. This has pi-0 order, or you can have 0 pi order where spins are parallel along x-axis and antiparallel along y-axis. These are the magnetically ordered states. Now there's also the tetragonal to orthorhombic transition, where the square lattice becomes rectangular here, and we also have domains. And again, what I want to talk today about is pairing. When I mean conventional or unconventional, I'm talking about is it phonon-mediated or not phonon-mediated, okay? So one of the important ingredients is that these are metals. So one way or another, we need to understand what is their Fermi surface. And then you ask your favorite DFT friend to do the calculation, and then you start having nightmares, because this is how the band structure looks like. And there's so many bands crossing the Fermi level. If you look at individual orbitals, you see that you have mostly x, y, x, z orbitals, but a little bit of x squared minus y squared as well. So this is very complicated. If you ask them to plot the actual Fermi surface, it looks a bit more friendly. This is in 3D. You see a hole pockets in the middle of the Brillouin zone, and electron pockets in the corners. And this is the reason why it's complicated is because of 3D6 configuration. So you have several, and the crystal field splitting is not that big. That means that you have more, you have several orbitals contributing to the Fermi surface. Now, we theorists we like to simplify things, and one way to understand this band structure is this one here. First of all, we just forget about the symmetries introduced by arsenic. They might be important, as I will argue later, and talk about the one ion pair in itself. Then we have one or more hole pockets in the center of the Brillouin zone. These are these pockets here. And displaced by pi 0, pi, we have an electron band here. Okay? This has to be C4 symmetric. These do not need to be because they are on the corners of the Brillouin zone. And this is, I argue, a minimal model if you want to start understanding these materials. Okay? And again, if you have questions, just ask. And now, let me go to the, okay.
Why in this picture the electron bands are on the edge, and in the previous one they were in the corner?
Well, because, let me quickly, I can draw this. It's easier if I draw. The reason is the following. If you are really, the real crystalline structure has, on a plane, you have iron on the square lattice, okay? If I just think about this, the unit cell is one of these blocks here, okay? And then it's this picture that I showed here. However, if I want to be more precise, arsenic sits either on top or below. I'm putting either a dot or a cross, okay? They're puckered. These two arsenics are above, these two are below.
No, Fermi-surface, no?
Yeah, but
and then,
but I mean first
space picture, and then
yeah, but the unit cell from the unit cell I find out what is the Brillouin zone, right?
Yeah.
That's what I'm doing.
Yeah.
So if I don't forget about the arsenic, the unit cell has one iron per unit cell is a square. Okay? Now, if I include the arsenic, which hybridizes with iron, okay, then the new unit cell is this guy here. Okay? Has 2 iron per unit cell, and it's rotated by 45 degrees. Okay? So the Brillouin zone is smaller and rotated. And if you do this operation, you obtain this guy here. Okay? So what I'm missing when I'm not putting arsenic, I'm missing arsenic hybridization, which may be important as I'll talk later. But I want to go slowly. Okay? And this is just a detail of the problem now. I don't want to go into there. Okay. So now let me finish lecture 1 by telling you what are the superconducting state phenomenologically, and then later tell you about microscopic models. So, how do I classify superconducting state? Well, as in every system that I have, as you heard from the lectures earlier, we need to understand how the wave function behaves under certain symmetry operations. And these are the most general operations that you can have. So U1 symmetry is a gauge symmetry that you always have to break if you want to have superconductivity. And that doesn't matter if you're conventional or unconventional. And I will go back to this point in the end of the talk to see how this is related to supercurrents. Okay? Very good. This is always broken, meaning that you form a Cooper pair. This was what you told you ordered today. Now, we need to classify how my Cooper pair wave function changes under time reversal operations, rotation operations, and crystal lattice symmetries. So if I'm going to forget about time reversal. I will only consider superconducting wave functions that don't break time reversal symmetry. The ones that do break are very interesting, but much rarer, much more rare. And we can talk about it later. So let me focus on rotations. In rotations, you can have if a crystal has inversion symmetry, which is the case of pnictides, I have 2 possible spin states, singlet or triplet. What does it mean? Well, I have 2 spin half electrons. When I combine them, I can have either spin 0, a singlet, or spin 1, a triplet. Okay? These are the 2 possibilities. Now, if I choose one of these 2, this is already going to constrain what kind of crystal lattice symmetries I can follow, because remember, the total wave function, these are 2 fermions. So the total wave function has to be antisymmetric if I exchange these 2 fermions. Now, singlet state, you remember very well from your quantum mechanics classes, is an antisymmetric state. Remember, singlet is spin 1 up, spin down, minus spin down, spin up. If you change up and down, you get a minus sign. Triplet, no, it is still symmetric. So if you have a singlet, and I now want to know how the wave function, what's the pairing of the wave function with respect to the crystal momentum, if it's singlet, I need to find combinations. I need to have even parity, such that the total wave function is antisymmetric. Even parity states, as you know very well, if I'm talking about the conserved angular momentum, so I'm going to say that I can have L equals 0, which is called S wave, L equals 2, which is called D wave, L equals 4, that's called F wave, and so on. Okay? G wave, I'm sorry. Thank you. Triplet, on the other hand, has to have odd parity, meaning that the wave function has to acquire a minus sign if I change k to minus k. Then I can have L equals 1, which is P wave, L equals 3, which is F wave, and so on. This is the language that you get from orbital physics. Okay? But again, it's only valid if I have a crystal inversion symmetry where I can classify as triplet or singlet. Okay? Very good. So now, if I want to be more specific, I need to tell you what is the point group symmetry of my lattice and discuss what are the possible representations of the wave function. They have to be one of the irreducible representations. So I will consider the simplest case of all, which is the square lattice. So I'm going to throw away z dependence. And I will consider there is no time reversal symmetry breaking, and that I'm in a singlet state. Singlet state is usually the one that has the highest DC. And I believe Gil will tell me more tomorrow about cases where you can have a triplet state. But most of the times we have singlet. Okay? And time reversal symmetry breaking is even more rare. So that's the majority of cases. So while you do your group theory class, and then you find out that what are the reducible representations of your square lattice. And you have these beautiful names, A1G, A2G, B1G, B2G. Okay, because we are very creative. Mathematicians are as creative as we condensed matter theorists. And of course, usually we refer them to their nickname, which is S-wave, G-wave, dx squared minus y squared dxy. But of course, this is a bit too abstract. So what you can do is just do a contour plot of all these functions. And then we see how the gap behaves. So this is if the group the wave function has A1G symmetry, it means that if I rotate it by 90 degrees, it looks the same. And I'm doing the particular representation of x squared plus y squared, which in this case is pretty much a circle. So what means is that the gap function is the same no matter what direction I look. That's the S wave that I discussed yesterday with you about the conventional superconductors. Okay? Now there are other possibilities. This is the G wave representation, and as you can see, is at A to G. If it's A here, it means that if you rotate by 90 degrees, you get the same figure, and you'll see that this is true. But now you can see that the gap alternates between plus, minus, and so on. And you have actually 4 line nodes. What are line nodes? Are these lines where the wave function is 0. Okay? Remember that a negative gap doesn't mean that it still means it's a bound state because the energy of the gap is the absolute value of delta. But the zeros will be very important, as I'll discuss later. Now this is a very popular one. If you study the cuprates, you've probably seen this one. This is dx squared minus y squared. It belongs to the B representation, B1G. So it means that you have to rotate by 180 degrees to obtain the same figure. Okay? Now you can see here, go from minus to minus, you have to rotate by 90 degrees. And you have 2 diagonal line nodes. Okay? Now there's another possible D wave, which is dxy, where the only difference that the nodes, the line nodes, instead of being diagonal, they are vertical and horizontal. Okay? But you go from plus, minus. Very good. Now, this is not the full story, because even in A1G, I can combine higher order harmonics. I can, for example, create the so-called extended S wave, or S plus minus, as I will tell you more very soon, where I still have A1G, meaning that I don't have any nodes crossing the 0. The nodes now are not in any way related to a high point, to a high symmetry point of the Brillouin zone, but I still have sign changing, plus, minus, plus. So if I rotate this by 90 degrees, I obtain the same figure. Okay? And I will claim that something like this is the superconducting state of most of the ionic tides, except some special ones possibly. Okay? And a key point that I want to make is that these zeros do not cross the gamma point or the x point. Okay? This will be important very soon. Okay, show you, this is phenomenology. I'm telling you what are the possibilities, just based on group theory. Now, what question do you ask me? See, I'm letting you ask any question. Except what is the score of Barcelona and Bayern? I don't know. I know some people here are missing, and I'm taking it. Oh no, you're here. Very good. I'm glad that you gave up the game. But other than that, what question would you ask? I'm showing all the possibilities. Which one do you think is the more likely to happen? Let me ask you a different question. You all solve quantum mechanics, one-dimensional quantum well. Right? What is the fundamental ground state? What is the wave function of the ground state? Does it have nodes? Does it have zeros of the wave function? What about you guys speak? I saw that lots of people doing that, but say yes, no, huh? Why not? Okay, that's not a fair question. Huh? What if I go to the first excited state? What happens to the wave function? You get how many nodes? Okay, what if I go to the second excited state? Very good. So, from all the states that I showed here, which one do you think should be the most likely to appear? There we only know nodes. Mostly because, why would I not gain as much energy as I want? Delta squared is the wave function. So why going to 0 to make delta 0 if I have delta non-zero everywhere? Right? But my claim is that both pnictides and cuprates, they have nodes. Why do you think, so these are representations in polar coordinates, it's the same thing. Why do you think the wave function, why do you think the gap function wants to vanish at some directions? Come on, just guess.
Minimization of energy or something.
Say it again?
To minimize the energy of the
To minimize energy, but how do you minimize the energy if it's proportional to delta squared? There is a key ingredient here. All that I told you yesterday, I had an attractive interaction, right? That formed a bound state. Now suppose that my interaction is attractive in some directions and repulsive in some other directions. Then I want to vanish the gap when it's repulsive, because I don't gain any energy there. And that's the main reason of why you want to have that. Ultimately, if you have a strong repulsion, you want to have the gap everything to 0. Okay? And you cannot acquire that with the S wave state. So what I'm trying to say is that with repulsive interactions, you can have a state that will usually not be just a 1D representation. Sorry, some question? No? Okay. So how do we have superconductivity from repulsive interactions? There are various theories, there are very different points of view. One of them is the RVB theory that I believe Tomo talked about yesterday. It was initially proposed by Anderson. There are now more and more numerical solutions of the Hubbard model involving the dynamical mean field theory, and there's no Tremblay talk. This is from a different school, I'm sorry. But anyway, look at Tremblay's paper. And another, which goes all the way back to Burke and Schrieffer in 1966, and was later put forward by Scalapino, then Pines, and many others, is pair-mediated by spin fluctuations. I'm not going to discuss which one is right for its system. Instead, I'm just going to talk more about this pair-mediated by spin fluctuations. You hear this all the time, and I want to tell you what it is. Okay? And the motivation is that in the phase diagram, you have superconductivity close to magnetic instability. Okay? That's the main motivation, as Pascual and Hondin said yesterday. Okay? Okay, so this is the parent compound of pnictides. I have this magnetically ordered state. How this magnetism can help me to have pairing? Well, I'll be a bit qualitative here, but just come with me here and accept just this more qualitative approach now. What are the excitations of any magnetic ground state that has continuous symmetry? They're spin waves. They're so-called magnons. So it's much easier to understand the concept in a ferromagnet, but it works for antiferromagnet or spin-less wave and so on, as long as it's a continuous symmetry. It's not Eisenline. In this case, for example, this is one of ground states of ferromagnet. It's a different ground state. I can try to start with this ground state and very slowly and weakly modulate a wave where the spins rotate from one ground state to the other. This costs me very little energy. These waves are called spin waves. You can see them here too, or here in an antiferromagnet. And they, as with any wave excitation, if you go to low temperatures, you quantize and they become bosons, and they're actually called magnons. Okay? They're excitations of the perfectly ordered magnetic state. And Premi told about them yesterday, a little bit. Now, this, in certain ways, is analogous to phonons, but to be a bit careful here. That's why I drew a one-dimensional lattice, because of other kinds of modes. But what I want to say is that if you have a lattice and you consider the vibrations around the equilibrium positions, you get waves that are the phonons. Okay? Remember that conventional superconductivity can exchange phonons. Can I get superconductivity exchanging magnons? Sounds interesting, but usually you can't. Especially because magnons only appear deep in the order state. But there's some cousin of the magnons called paramagnons that appear in the paramagnetic state when you have a metallic antiferromagnet. You can understand there as these spin excitations get gapped in the paramagnetic phase, but they also, because you have a Fermi surface, a spin excitation decays in a particle-hole pair, and this causes something over them. I don't want to go into details, but this is important because if you have magnons, the coupling of the spin and the spin excitations and the electrons goes to 0 at Q equals 0, and you don't get high DC. With paramagnet situation, slightly different. Okay? So the analogy is this one. Instead of exchanging a phonon, what the electrons exchange would be a spin fluctuation mode, which in most of the metallic magnets, antiferromagnets, is a paramagnet. Okay? And the idea is that this can be the glue for the pairing state. Okay? What is the complication here with this analogy, with the phonon case and the magnetic excitation case? What was special about the phonons that I told you yesterday? That I said that we can understand very well the Eliashberg theory, we can throw away vertex corrections. There's Migdal theorem that guarantees us that. There was one thing that I told you was very important there. Remember? What was that?
Mass nucleus, the ratio of mass.
Yes, there was a small parameter which was energy scale of the phonons, energy scale of the electrons, right? It's a small parameter. And mostly because phonons are not electronic excitations. They're lattice excitations. They're independent. Now, spin fluctuations are electronic excitations. They come from the same electrons that are being paired. This adds a very important complication to the problem, but also interesting possibilities. Okay? Because you don't have a natural small scale anymore. And this has an important feedback effect, that the same objects that are being paired are the ones that are causing the pairing. So this is one argument of why TC could be going up. Okay? So this is the qualitative view of spin fluctuation pairing. And I'll go into a bit more details. Before I go there, I want to know if there's any question about this qualitative view. Okay. Who has a microphone? No one? That's fine. Let's just pass here. Can you pass to the next one then?
Okay. So you said that using basic quantum mechanics, you should have a S-wave gap in the Fermi surface.
No, I said no. That's not what I said. I said that if you solve the quantum well, the ground state has no nodes.
Yeah. Okay, perfect. But then in these materials, in the cuprates and the pnictides, you have the sign of the changing, being repulsive.
Yeah, I will go. Yeah, okay.
Okay, and the question is why?
Well, I'll go to this right away. Yeah.
Could you explain more about the difference between magnons and paramagnons? I didn't quite understand that.
Well, I don't want to go into too many details, but the main difference, if you want to know a bit more details, the difference is in the propagator. Okay, one is overdamped, the other is propagating, and that gives a very important difference. Okay, so if you want to know more details, the propagator of a paramagnet is something like this. There is a gap plus Q squared minus I omega over gamma. This is the damping factor. This comes because your spin excitation, there's a Fermi surface there. The low energy excitations around the Fermi surface are particle hole pairs. Your spin excitation can indicate a particle hole pair. That's called Landau damping. Okay? And that gives rise to this here. If you don't have this here, you would have a minus omega squared. Okay? That gives propagating waves that are damped, that are gapped, sorry. Okay? But I don't want to go into these details. And remember, the magnon, the energy of the excitation goes to zero as Q goes to zero, Goldstone theorem. While in the paramagnetic state, these excitations are gapped. Okay. Other questions? So in one case, I have a wave, and the other is like it's just an overdamped decay. Okay. Okay. So let me tell you a bit more. So one thing that I have here, but I think it's going to be too many details, is how to derive this expression. Okay? This relates how the pair interaction is associated with the spin fluctuation spectrum. This is just the spin susceptibility. Okay? This can be derived from a diagrammatic perspective, but I think it's too technical. I will not go there. If you want to know more details, I have detailed notes that I prepared and I can share with you. Okay? But you can derive that. The key point is that there's no minus sign here. Remember, if I had charge, if I had phonons, I had a minus here. In this case, I don't. And the reason is because you're not coupling charge, but you're coupling spins. And Gil Lonsdorf, this is a picture from one of Gil's paper. He's not here, but I'm almost sure he will talk about it tomorrow. So don't get hung up on the fact that I didn't prove that. Let's start from there and see what happens, okay? So the pair interaction is proportional for singlet to the spin susceptibility here. Now, the spin susceptibility, if I have an antiferromagnet, it has a modulation vector. Just plus and minus, like I'm plotting here. It's repulsive in the origin and then decays. Okay? So this means that I want to view the wave function that vanishes at the points where I have repulsion and is maximum at the points where I have attraction. Alright? Now this is a one-dimensional picture. Let me be a bit more precise. Let me go to a two-dimensional picture. This again from Gil's paper. It's a nice, very nice review. And then, if I have just a square lattice, an antiferromagnet with order vector pi, you can just calculate the real space susceptibility, and you find out that you start with negative here, attraction here, repulsion here, attraction here, repulsion here, and so on. And in particular, you see that you have two lines where you only have repulsion. How do you minimize your wave function, or how do you maximize your energy gain? You minimize it by vanishing the wave function here, because there's no attraction. If you vanish the gap here, you see that you get something that looks like a dx squared minus y squared wave. And that is one of the, this was in the early days of the cuprates, one of the proposals that why this would be a d-wave superconducting state. Okay? Now, if you have to do real space analysis for each ordering vector in each lattice, it will become a bit painful. It's much easier to look in momentum space. Then you look in the first grid ones up. Momentum space, it's always repulsive, right? And it's usually peaked at the ordering vector of your magnetic moment, of your magnetic ordered state, which in this square lattice that I showed you is pi, but in the nictide is pi 0. Okay? So you have a well-defined repulsive interaction in momentum space. Now what do you want to do? You want to solve the gap equations, remember? Gap equations that I wrote yesterday. Now, I will do BCS-like gap equations, meaning that I'm doing a BCS approach for spin fluctuation. There are dangers there, but nevertheless, let's just do it for now. And remember, I have the pair interaction connecting gap at momentum k to gap at momentum k prime. right? Forget about these guys here. They're all positive. There's a minus sign here. If I have attraction, V is negative, I can put delta independent of K and K prime and solve that's the S rate. And if I have a repulsion peak that K prime equals K plus B cubed, then you'll find out that the only way of solving this is if I change the sign of my wave function from K to K plus Q. Then I can solve this equation, because this V is peaked at Q. Now, what do? You go to the Fermi surface. This is a Fermi surface on the square lattice with nearest neighbor and next nearest neighbor interactions. And then you see the points are separated by Q. You want to change the sign from plus to minus. You build your function, you find that you have to have zeros because of diagonals. This is the D wave. Okay? That's another way of finding the wave without having to plot your susceptibility in real space. And that's the usual strategy in spin fluctuation. You see where your repulsive interaction is peaked. Okay, what is that momentum? And you want to change the sign of the gap function from that momentum to the other one. And that usually gives rise to zeros of the gap function. Okay? Any questions? The microphone? Okay.
I guess I'm just confused on that. Where does chi-s come from? When you
Chi-s is this?
integrate out?
Huh?
You integrate something out to get chi-s? Or-
Well, I mean, there's several ways that you can try to get, right? Chi-s is just the spin susceptibility, right? So you can calculate from your low energy model as just being the bubble, right? The GG, the product of two Green's functions, okay?
How does that come from pairs?
Well, that's what I'm not showing to you, because that requires, I mean, I have the notes, but it's going to take me at least 2 hours. And I don't want to go there. To go into all details. I can show you later, it's not complicated. But if you do the diagram, the equivalent, the diagrammatic coupling spin fluctuations to electrons, looking at the pairing channel, you find out that the pairing is repulsive and is proportional to the spin fluctuation at momentum Q. Okay? There's some assumptions there. I can discuss this more. But that is the result if you do some microscopic model. Just do diagrammatics, coupling electrons to spin fluctuations. There's you can go to a low energy model where you assume that you have spin fluctuations because you're near magnetically ordered state, and couple these modes with your electrons, and then just calculate self-energy and so on, and the pairing amplitude and see where it diverges. Okay, that's the way to go in this with a weak coupling approach. Okay? So, and then you find out that it's proportional to the spin susceptibility, which is nothing but the propagator of the bosons. Okay? Any other questions? Because now I will apply this to the nuclides and discuss the pairing state. Can you? Yeah.
So the Q here is not commensurate, or?
No, here, no, it is. It's pi, right? This Q here is pi. If I put it on the gamma point, it's going to connect me to the M point. I just displaced it because only states near the Fermi surface will form a Cooper pair, according to this model, okay? That's why I just displaced it, okay?
How about the strong coupling approach?
Well, that's another way of doing that. That's what Hongding was talking about, for example. You can start with a J1, J2 model, with J model, where Heisenberg model, and you project your operators in the pairing channel, and you find the corresponding pair interaction. Not surprisingly, if you do that, you get the wave as well. Okay? I'm not going to go into the discussion of which one is the best approach. In the Cooperates, one is approaching the right, the other is approaching left. I'm not going to go to the discussion there. I'm just discussing what is this particular model, okay? But in both cases, you have magnetic energy scale playing the main role. Okay? Other questions? Okay, so now that you saw that, what happens in the nuclides? Remember, that's a Fermi surface of nuclides. It's disconnected. I have one whole pocket, and the electron pocket is displaced by pi 0, 0, pi. Now, Igor Mas in the early days calculated the spin susceptibility, and he saw that it was peaked at the ordering vector pi 0, 0, pi. Okay? So we're going to play the same game, and I'll do this on the board now. So you wake up. Because I don't have pictures of me in a band. So. Você pode levantar para mim? Okay, so what's the idea? Well, since I'm a theorist, I will use the prerogatives that Pascal told that we have, and I'll simplify the model as much as I can. So I'll just look at two bands. Okay? I have one band at momentum 0, 0, and another band at momentum pi 0. Okay? And my Brillouin zone is over here. It doesn't matter. Okay? It's two-band model. Now, I have a repulsive interaction connecting these two, picked at this order vector. I'm going to call this V. Okay? And I want to find the gap at this band, which I'm going to call delta 1, and the gap at this band that I'm going to call delta 2. Okay? So this is just a BCS-like two-band model. So how do you do that now? Well, let me write down the BCS equations, right? So it's the same that I wrote for a single band, but now I have to couple band 1 with band 2. Remember that the BCS equation was delta was equal to, and now I'm going to write this near TC, because I want to find what is the leading instability. Near TC, this was the equation that I had. Roughly. Sorry. That was the equation that I had near TC. It was just that equation solved when sending delta to 0. I have pairing V, density of state rho F, this is a number, that's a coupling constant. Delta on one side, delta on the other side, and a log that gives me TC. W is just some energy scale beyond which there's no attraction anymore. Okay? And that, of course, this was absolute value. And then delta goes away, and you find TC. That's what we did in yesterday. Now here, I have to couple band 1 with band 2. So the gap at band 1 will depend on the gap at band 2. So it's going to be minus V. Remember, I had a minus, but I had attraction in the single band model. Rho F, delta 2 log W over TC. Please stop me if you don't understand, okay? Can go back some steps. Now, okay. But now I have an equation for band 2 interacting with band 1, which is equivalent. Right? And I need to solve this 2x2 system of equations. I want to have 5 bands. This is going to be 5 by 5. It's easy. The 2x2 is easier from my point. Now you can always write this equation, okay, in the simplified form here. I can always write this as delta 1, delta 2 equals log W over delta TC. I'm now writing matrix form. Okay. Now this matrix here, delta 1 couples to delta 2. Sorry. So it's 0 minus V. Of course, density of states of band 2 and 1. That's important. Rho 2, rho 1, 0. This is just matrix form of this 2x2 system of equations.
For that, you assume that the coupling just happens between particles of different.
I'm using that expression,
Okay.
and I'm making a further approximation that it's strongly peaked at the ordering vector by 0.
I see.
Okay.
Because in the general case, we also would have diagonal terms.
Yes, and that's important because of repulsion, and I will go Very soon. I first want to solve the easier case, then I will add intraband and interband repulsion. Okay? So this is a very good question, but I'm just building slowly. Okay? Any other questions? Very good. So this is matrix equation. How do I find TC? Well, now it's easy. All I need to do is find the eigenvalues of this matrix. I will have 2, of course. So I'll find 2 values of TC. Which one is the bigger is the one that will be realized. But which kind of state will be realized? Well, that depends on the eigenvector of the largest eigenvalue. Okay? What I'm saying is that if I find the eigenvalues of this matrix here, then all I need to do is that the eigenvalue times this guy is equals 1. So let me call lambda the eigenvalue. I have 2, okay? Then what I will have is log times lambda must be equals 1. Then I solve this equation. Do you agree with me? Okay? And then I find that TC is W e to the minus 1 over lambda. Okay? Just solve this equation here. Now, in order for this to be true, lambda has to be positive. I cannot have a negative eigenvalue. Right? Because TC is always smaller than W. So if lambda is negative, this equation can never be satisfied. If I have 2 lambdas positive, which one wins? The one that is largest. Okay? So that's how you find the ground state, superconducting state of multi-band models. Okay. Eigenband, go ahead.
Is it possible that one band becomes superconducting and the other doesn't?
Not in this case. Okay? And the reason is because they're coupled via the V. If they were uncoupled, yes. But there's always, this is called a Josephson coupling, although I think the name is a bit misleading because it's just a momentum coupling, okay? So in this case, no, they have to become superconducting at the same temperature. And that's general for multi-band systems because they're always coupled, okay? Now, you guys are masters in algebra. What are the eigenvalues and eigenvectors of that 2x2 matrix? The winner gets a free drink in the poster session. I promise. Okay.
Square root of the 2 diagonals.
Very good. So I have 2 eigenvalues, which I'm going to call lambda plus and lambda minus, which is plus or minus V, or sorry, I should put, let me just put like this, okay? That's the eigenvalue, okay? For the plus, the eigenvector, the eigenvector is always defined up to a constant, so I can define them as the ratio delta 1 over delta 2. So plus and minus will be minus or plus square root of rho 2 over rho 1. Okay? So these are the eigenvalues. I'm lazy to write eigenvalues, so I put EG. And these are the eigenvectors. Okay? If you don't believe me, go to your Mathematica and just type this matrix, and that's I system, full simplified, and you'll find this out. Okay? Very good.